Okay, so hello everyone, welcome to today's Maths Club Talk. Today's speaker is Suvadip. He is an M.Math second year student. So he has been a part of ISI Bangalore for 5 years and has been the hand behind many developments and events here. In fact, he is also one of the founding members of the Math Club and has been a regular speaker over here. So his research interests are probability theory, high dimensional statistics, machine learning, and applied probability theory. So today's topic is Introduction to Ergodic Theory. And if you have any doubt in between the talk, like you have any questions, you can unmute yourself and ask it directly or post it on the chat and we'll convey it to him. Okay, so now over to you, Suvadip.
Thank you, Snail, for the introduction. I hope you can hear me.
Yes, you're audible.
Okay, so yeah, first of all, thanks to everyone for coming in this Sunday morning. Okay, so I'll just share my screen. Can you see my screen? Anyone can confirm? Okay, cool. So fine. So let me start it. So just give me 1 minute. So can you see any line that I draw?
Yeah.
Okay, cool. Okay, fine. Okay, so I'm going to talk about ergodic theory, and it's a very delicate subject because it involves a lot of technical tools from other areas of mathematics, like measure theory, especially complex analysis, even a lot of probability theory. So this is a very basic talk. I think it's quite accessible to the B.Math, and it's also accessible to anyone with a basic understanding of analysis, probability theory, and a bit of open sets and closed sets. So I'm just going to briefly talk about the history. Okay. So the history it goes back to 1880s. Okay, so it started with Boltzmann. So okay, so he was quite interested in looking in statistical properties of large dynamical systems. So and he looked at very complex problems. So I'm not going to talk about like what he looked at, but I'm going to give you a very simple motivation of it. So a very and by the way, this Boltzmann is a very famous, I think he's an Austrian physicist, and he is a very famous statistical physicist. I think he has a lot of results under his name. So, I'm not going to look at the motivation that Boltzmann had, but I'm just going to look at like a very primitive, or rather a quite elegant motivation, I would say. So from probability theory, we know a very classical result, right? Strong law of large numbers. So I think this is taught in probability 1. So if you have, let's say, x1, x2, xn, IID, IID x, so x1 and x2 up to xn all are independent and they are distributed as x, and they have finite mean. Okay. So then the strong law of large numbers states that this x1 plus x2 plus xn over n goes to expectation of x1, right? This is a very fundamental result from probability theory. But now let's look at this result in a bit different way. So we'll look at this quantity and look at this quantity separately. Okay, so this is what is known as the time average. So I'll just explain how it is the time average and all. And this is what is called the space average. Okay. So the space average. So how is it like like a time average. So you imagine like at each so imagine this is like the time point. Okay. So so you have like at one, like you have discrete time points 1 2 3 4 and so on up to n and so on. So at each time point you observe an ID random variable x1 x2 x3 and x4 and so on, so xn and so on. So if you take the average of these first n quantities, that gives you the time average up to n points. And this is the space average. So if you know a little bit of measure theory or a little bit of probability, you'll know that this is nothing but you integrate over the sample space with respect to your probability measure. So this is your space, like your sample space. Okay. Okay, just to confirm, can you all hear me? Anyone can confirm?
Yes, you're audible.
Okay. 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 Cool. Okay. So this is the sample space. Okay. So this integration is just a replacement of sum. This is so you're integrating this random variable x over the space over the sample space. So this is the space average in that sense, and this is the time average. So your strong law of last number states that in the limit your time average is equal to the space average. So this is a very special case of what we look in general. So okay, sorry. So 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 uh, so this SLN is a very special case. Is a very special case of a general class of theorems, which are called ergodic theorems, that I might talk in the end. It's a very special case. So we are interested in looking like when in the limit, uh, so these are all vague terms. Okay, I'll define as I go along in the lecture. So when in the limit you have like time average sort of approximate as n tends to infinite equal to space average. So this is a type of question, the one type of question that ergodic theory tries to answer, and we'll look at this as we go along the lecture. This is one motivation. So now let us look at imagine imagine you have a closed space. Okay, it's a finite space. You can consider a box in R2 or R3. Even actually Boltzmann looked at box in R3, but his dimension was quite high, so I'm not talking about his example. So I'm just going to simplify that and talk about it. So this is, so you consider a box in R2, and now imagine a particle. So this is a box. Okay. So now imagine a particle inside the box X, and let's say and then you have time point. Let's say 1. So at 0, at 0 the position of the particle inside the box is at x, and at 1, at 2, 3, and so on. So and a force is acting on the particle x at discrete time. So let t be the force acting on the particle x. At discrete time points. Okay, at discrete time points. So, so at 0, the position of the particle is at x, and you have then at time 1 you apply uh, uh, the force T on the particle x, and it moves to some this position T of x. Then similarly at time 2 you apply a T to the particle at the position T of x, so it moves to T square x. So something over here. And then again at time 3 you apply T3 of x, so on and so on. So you have Tn of x. So this particle moves under the influence of this force T. So in group theory, you must have learned something which is called an orbit of an element. So here you also have something called an orbit of set X. So orbit of the set X is nothing but all this collection, X, dx, t squared X, and so on. So I can write that as Tn of X and less than equal to 0. So T0 of X is nothing but it's just the identity map, just an X. So yeah, so this is the setup. Now, what are the interesting questions to ask over here? So the first question to ask, first question, is suppose you take a random set inside this box. So you have X, and this is, let's say, A. So this is your box X, and this is your random. So A is a subset of X. Now, the one interesting question to ask is, does every particle inside the box X will visit A or not? So here we started with one particle X. Suppose you have another particle Y, and it moves under the force T. So it goes to T of Y. Then again it goes to, let's say, T square of Y. The question is whether it will hit A or not. So there are infinitely many particles inside the box. So, and each is moving under the force T. So the question to ask is, does every particle inside the box X will visit A in the limit, let's say. This is one question to ask. And second question is to ask is, does the number of visits have some average limiting average properties, some limiting average properties. So what I mean by this is, if I look at this quantity, so indicator of A of Ti of X. So this is nothing but the like the number of times the particle X visits A up to n minus 1 time points. Okay. So now if I divide this by n, so since we have n quantities, the question is, do we have convergence? Do we have convergence? And if we do, and if we do have convergence, then what is the limit? Then what is the limit? Yeah. So these are very natural mathematical questions. So yeah. So we have these two motivation. So, and for the second motivation, the first question is answered by a theorem in ergodic theory, which is called the Poincare recurrence. This theorem will prove, and the second question is answered by an ergodic theory, which is an ergodic theorem, which is a very fundamental result in ergodic theory, which is called Birkhoff Ergodic Theorem. And it has found numerous applications in ranging from information theory, probability theory, and even in general stochastic processes of dynamical systems. So, okay. So yeah, so we'll try to answer this type of questions. All right. Okay, so this was the motivation. So okay, so now I'll move on to the next topic, which is there's something called the setup. Like now we'll try to do rigorously. So now it's the setup. So okay, so let me just stop for like 10 seconds and let me see if you have any questions. So if anybody has any question, please ask about motivation or anything. You can hear me, right?
Yes.
Okay. Okay. So if anybody has any question, can ask right now. Okay. If not, I'll just move on. Okay. So the setup is it's quite, I'd say, measure theoretic. So the setup is quite measure theoretic. Okay. So I sent the prerequisites, of some of the basic measure theory stuffs. So I'll just briefly recall. So you have an X. So most X we take it as is a metric space. So metric space. And sometimes we just restrict our X to be compact metric space. Okay, so we have X, and F is a sigma algebra. Okay, so sigma algebra has a property that first property is that the full X belongs to. So the sigma algebra is a collection of subsets of X. So the first property that sigma algebra has is that X belongs to script F. Second is if A belongs to script F, then we'll have A complement also belong to script F. And third is if you have a countable collection of elements such that each AI belong to script F, this will imply your union AI also belong to script F. So this is the definition of the sigma algebra, and you have a measure. So you have a measure. So what is a measure? Measure is nothing but a function from your sigma algebra to your positive real line, but it can also take infinity as values. So it can also take infinity as values, and the two properties it has is that mu of phi is 0 and mu of a union of AI is equal to sum over I going to 1 to infinity for AI intersection AJ I not equal to J. So for mutually disjoint events, this mu is like this property is called countable additivity. So this triplet over here, is called a measure space. Okay, it's called a measure space. And if you don't have this measure mu, then if I just look at this, it's called a measurable space. Okay, these are just terminology. And if we have the measure of X to be okay, to be 1, then this space X is called a probability space. It's called a probability space, and we'll restrict. Oh, okay, I'll just write first, and we will restrict all our results to. So we'll restrict all our results to probability space. So whenever I say I have a measure space, something like this, you just by default assume that mu of X is equal to 1. Okay. So and it can also happen that sometimes mu of X is finite, but any finite measure is sort of equivalent to a probability measure because you can redefine a new measure as something like mu of A over mu of X. then this mu prime is a probability measure. So every finite measure have the same properties as probability measures. So better to look at probability measures. So this is the setup. So very basic setup. Now I'm going to talk about something which is called measure preserving transformation. Write MPT, measure preserving transformation. Yeah. So yeah, I'll just write it fully. So this measure preserving transformation. So what is it? So suppose you have a map from X to X. By map, I mean this T is measurable. So T is measurable. So what does measurability means? So in the background, you already have, so by X, I mean this triplet only. Okay. So I'm just not writing fully to like to just avoid, just like a lot of space. So T is measurable. It just means that T inverse of A belong to script A for all A belong to script F. This is just a definition of measurability. So, so any continuous map you'll see is sort of measurable. I uploaded a prerequisite. It's over there. So any continuous map is a measurable map. So okay, suppose you have a map now T from X to X, and measure preserving transformation means like mu of T inverse of A is equal to mu of A for all A belonging to sigma algebra F. So the like this now might sound like a very abstract definition, but this is like it's a very magical definition. You have a lot of consequences and beautiful theorems coming out of it. So in probability theory, just by using independence, you have a lot of beautiful results. And in ergodic theory, you just assume measure preserving transformation, you have a lot of beautiful results. So from measure theory, if you assume independence, I think you branch out to probability theory, and if you have like measure preserving transformation, you come to ergodic theory. So now okay. So the motivation of this definition, let's say. So just note, like suppose you have a box and you have another box. Okay. So, and there's a map. So this is X. This is X. This is a map T. This is a map T. Yeah. It's kind of connected. I don't want connected things. This is T. Okay. So now you have a particle over here X, and you apply T, and it goes, and it takes X to some T of X. So T is just a transformation which takes every particle in the box to some other position, like in the box. So suppose, let's say this is so an ideal gas. Let's say an ideal gas, right? So I think an ideal gas, I think, cannot be compressed or something. So so while having a transformation of the ideal gas, you want such a map which doesn't change the volume or pressures and other measure present in the ideal gas. So this quantity just reflects that. It doesn't allow the medium to compress or dilate and all. So this property just captures that philosophy set. Okay, so this is so now you have a metric space, a sigma algebra, uh, a measure, and a measure preserving transformation. So this quadruple is what is known as a dynamical system. So in ergodic theory, you study this type of dynamical systems. Okay. So again, so this T is measure preserving. That means this T follows, this measure preservingness. Okay. Now let's look at some basic example that you can very easily check. Okay. So this is something called a doubling map. It's a very famous examples. Doubling map. So you take x to be 0, 1 and script f to be your Borel sigma algebra. So Borel sigma algebra means just the sigma algebra generated by all the open sets in this set X. So the sigma algebra generated by open set means the smallest sigma algebra which contains all the open sets. You can have a look at my prerequisite for more information. Yeah. So and your measure is it's called a Lebesgue measure. The Lebesgue measure on the space X. So this Lebesgue measure has a very beautiful natural property is that if you take any interval, it has like what you expect, b minus a. And so now we want to define a measure preserving transformation t. So let's define from x to x. So you take an element a, you send it to twice of.
Your screen is not visible right now. It just got disconnected. The one.
Okay, okay, just 1 minute. Okay, can you see now?
Yeah.
Okay, so can you just tell me like from where it's got disconnected?
Oh, it just got disconnected just now.
Oh, okay, cool. Yeah, thanks for telling me. Okay, so now so now you have the Lebesgue measure mu, and now we want to define a measure preserving transformation. So from x to x, we define a map, a going to twice of a. So look, if you have just twice of a, then you are going out of the space. So let's say if you have 3 by 4, and if you just double it, you have 6 by 4. But you don't have 6 by 4 in this space, 0, 1, right? So what you have to do is you have to take mod of 1. So by mod 1, I mean take minus 1. So you have is that in half. Yeah, it's in half. So and like yeah, but if you have let's say 1 by 4, it's fine, right? Like if you take double of that, it gets 1 by 2. So you keep intact. So I write t of a is equal to a twice of a if a less than half and 2 if your a is greater than equal to half. Okay, so this is your map. Okay, so now I don't know whether I should give it as an exercise to check like whether it's a measure preserving or not, but I'm just going to give you a sketch of it. Like yes, it indeed is a measure preserving transformation. So you have the space 0 and 1, and over here also you have sorry. So sketch of the proof that it's indeed a measure preserving transformation. So you have 0 and 1, 0 and 1. So for a less than half, you're going something like this, and then from half to 1, you're going something like this. Okay. Oops. This is your map T. Okay. So now, first we'll show that for any interval. So if I take any interval here, okay. So if I just project it over here, it will have P image lying over here. You'll have a P image. Sorry, coming over. So you have a pre-image from there. Yeah. So this interval, say a comma b. Okay. So a comma b. We'll have two pre-images if you can check. It will be a by 2, b by 2, union a plus 1 by 2, b plus 1 by 2 union. like you just have to check it. So if you take mu of T inverse of A comma B, it will be nothing but B minus A by 2 plus B plus 1 minus A plus 1 by 2, which is nothing but B minus A, and which is nothing but the measure of this interval. Okay. So now, like you have just showed that like T is only measuring for those intervals. So similarly you can prove it for disjoint intervals, and then you can go to the general sigma algebras by some very basic theorems in measure theory that I've explained in the prerequisites. So I'm not going to talk about that because it will take a lot of my time. I have very small time. So this is one example, and another very standard example is the rotation. Okay, so rotation of the circle. Rotation of the circle. R mod Z. Okay. So R mod is nothing but S1, right? So let theta belongs to, I don't think anything, belongs to R, let's say. And you consider the rotation of T from R mod Z to R mod Z. You take X, send it to X plus theta mod 1. Okay, so it's just something like you have a circle, uh, you have a X, you have some e to the power I X, let's say, and you are moving by some theta, which is e to the power I X plus theta, something like that. So it's very clear geometrically that it's, so if you have an interval over here, you rotate it by theta, you go over here, something like this. The length is always presumed. So it's very clear intuitively, so that this rotation d theta preserves Lebesgue measure. Okay, Lebesgue measure. So yeah, so we'll come back to these examples later. I'll need all these, examples later. So now I'll move on to something called Poincare recurrence. So if you have any question now, please ask. I'll just wait for maybe 10 seconds. And can you hear me? Anyone can confirm?
Why is the definition of measure Poisson transformation not mu of TA equal to mu of A?
Oh yeah, that's actually a very good question. Yeah, very nice. Yeah, so your question is why mu of TA is not equal to mu of A, right? That is your question, right?
Yeah.
So okay, so let's say let's say okay, so consider this doubling map example. Let's consider this doubling map example like the same setup, and you consider the map from X to X. You go from, you take X to, okay, so 1 minute, sorry, so okay, so consider this example of doubling map. So now consider this interval 0 and 1 by 4. Okay, so if you just look at T of 0 comma 1 by 4 is nothing but 0 comma half, right? But the measure of T of 0 comma 1 by 4 is not equal to measure of 0 comma 1 by half, right? So this is So for this map, this type of maps are very important, as we will see later. So for this map to be sort of sort of preserving volume and all, you must have this definition, right? You have you must have this definition. And another reason for having this definition rather than this definition, like you have very interesting properties when you assume this rather than this. Okay, so it's just a consequence of your richness of the theory that you get just by assuming mu of t inverse of A equal to mu of A. It's just nothing special about it. But we want some maps to be measure preserving, and people have seen like having this definition is actually much more helping than than this definition of like what you said. And another from philosophical point of view, people always bring that the f inverse always behave much nicely compared to f, because you have f inverse of alpha as something like this and all, and it's true for intersection and complements and all. But for f of something like this, you may not have intersection of something like this. So this inverse map behaves quite nicely compared to normal maps. So it's just a convention, and people have seen like having this definition is helping a lot of it's helping in enriching the theory, and you're getting a lot of beautiful theorems. So they assume this definition rather than this. It's a pure kind of a convention, or I say experimental thing that have come historically and all. Definitions get modified in mathematics. So maybe people might have thought a lot of other definitions, but ultimately they have come to this definition, and they have found this definition is quite useful. I think you can similarly ask the question of sigma algebra. Why the definition of sigma algebra was like that? And why the definition of sigma algebra is like this? It's because people have realized that having this definition is quite useful and is giving you a lot of theories. And for more exposure to this, I think there's a famous book by Peter Walker's called Introduction to Ergodic Theory. You can have a look at that. So yeah, it's a very nice question. Thanks for asking. So does that answer your question? Sure.
Yeah. Thank you.
So does anybody have any other questions? Okay. So let's dive into the next topic. It's called Poincare recurrence. So now, as I mentioned in the beginning, so let's go to the motivation part again. So now look at this question. So you have this box X, and the same setup X is going to Tx, and then T is going to T square X, and T is going to T cube X, and so on. And you take a random set A, and you want to ask the question, does every particle inside the box X will visit A? So as I mentioned, the answer will be given by the Poincare recurrence. So that's what I'm going to prove now. So now I think this is the only complete proof in my talk right now that I'm going to give. So you have this setup, right? So you have this setup of dynamical system, and you have this measure of X to be equal to 1. I've assumed like this will be our convention. Right. So now this is known as the Poincare recurrence. It's the Poincare recurrence. Now here you will see why this inverse, how the measure preserving transformation comes into picture. Poincare recurrence is one of the first results proved in ergodic theory. Okay, and people use this kind of this Poincare recurrence in I think a lot of areas of mathematics, like in number theory, information theory, and all. So I think I recently saw an example in representation theory where you're using some representation of S52 and then S52, I think, and then you're applying some Poincare recurrence, though I don't understand that fully. So let's look at what a Poincare recurrence is. So this is your dynamical system, and T is a map definitely from X to X, and it's measure preserving. So mu of T inverse of A is equal to mu of A for all A belong to script F. Now, so what is the theorem? That suppose you have a set which belongs to script F such that mu of A is greater than 0. This is very much required. You need to have something which has positive measure. So I think in my abstract I mentioned, like, does every particle possess some nice subsets of X? So by niceness I mean this, that you have positive measure. This is the meaning of niceness in my abstract. Okay, so suppose you have a set which has positive measure, then for all, I should not say for all because we are in a measure theory setup. So almost surely, for all X belonging to X, there exists a tau X, which is a natural number, of course, such that T of tau X belongs to A. So many of you may not be understanding what is this almost everywhere or almost surely means. So I'll just write it down. So let A naught be the set of all X which does not visit A at all. Okay, so Tn of X does not belong to A for all n greater than equal to A. So by almost everywhere, I mean mu of A naught should be equal to 0. Okay.
Excuse me,
equal to 0.
in that definition is t power tau x of x belongs to A. Will that be the thing?
Yeah, right. Thank you.
Okay.
Yes. Yeah, thanks a lot. Yeah, otherwise it doesn't make sense. Yeah, thanks a lot. Okay, so we have A naught. We have so we look at all X such that Tnx doesn't belong to A for all n greater than equal to 1. If you can prove mu of A naught equal to 0, then you're done. And the statement of the theorem is done. And almost surely every point in X, like, it will visit A. So this is the theorem we want to prove. And here you will see that how this the measure preserving transformation comes into picture, and how helpful is it. So this is a very, initially it might seem like a very non-trivial theorem, okay, but it's not. If you see the proof, I'll do the proof, you'll see it'll just like 7 or 8 lines maybe, and it beautifully comes from this measure preserving transformation S. Okay, so you have this A naught. Okay, so now the proof. Okay, so define An to be Tn of A naught. Okay. So this basically means you're collecting all y, so Tn of y belongs to A naught. So first lemma. So the first lemma is a very easy lemma to prove. I could have just leave it for exercise, but I said for completeness I'll do it. So let's see, you have A intersection is empty for all
I
I
don't know
greater than
if
equal
I
to
am
0.
having a problem. Yeah, so I don't know if I am having a problem. Okay, so there was some lag. Okay, it's all right.
Okay. Now can you hear me?
Yeah.
Hello. Okay. 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 Cool. Okay. So. Okay. So now this is the lemma that you want to prove. Like this AI intersection AJ is empty. Okay. Okay. Am I sharing the screen right now?
Yeah, it's visible.
Okay. Okay. So can you see my OneNote?
Yeah, I can see it.
Okay, okay, cool. Thanks. Okay. Okay, so we want to prove this lemma, and it's actually a very easy one to prove. So that's proof of the lemma. So I is greater than j. So suppose let y belongs to a of j. So this will imply that t y sorry imply that tj of y belonging to a naught. But according to the definition of a naught, like for any n, you cannot have tnx belonging to a. So this will imply that t of I minus j, since I is greater than j, I minus j is a natural number. So j of y uh, should not belong to a naught. So this will imply t of I of y should not belong to a naught. Uh, but that's a contradiction, right? That's a contradiction because we already have this. Okay, so you assume, sorry, y belonging to aj intersection ai. So that will automatically imply that y belongs to aj, and from there you now use this. So since y also belongs to ai, this implies that t of I belongs to a naught. But this statement and this statement cannot go simultaneously, right? That's a contradiction. So, this lemma is true, right? Now it's on. You're done almost because so you're uh, so note that your n going from 1 to infinity, a of n is contained in x, right? They are just subset of x. So if you, by the monotonicity of the measure, just take mu of a and x, then this is less than equal to mu of x. So which is just by using lemma, you have summation and going to 1 to n mu of an. And what is mu of x? It's 1, right? We already assume it to be 1. Okay. So now note, like an is equal to t inverse of a naught. Sorry, t, uh, t to the power minus n of a naught. So note that mu of t inverse of a naught is equal to mu of a naught just by the measure preservingness. Right? Similarly, you will have t to the power minus 2 of a naught is same as uh, t inverse of a naught just by repeatedly applying this measure preservingness. Have this and then by induction, you will have uh, mu of t inverse of a naught to be equal to mu of a naught, right, for all n greater than equal to 1. But now if we have this and we already got this, right? So we already got something like this. Mu of n is less than equal to 1. this is nothing but less than equal to mu of t inverse of t n inverse of a naught is less than equal to 1. But now this result will give us mu of a naught is less than equal to 1. See, if mu of a naught is positive, then this quantity blows up. So this quantity will go to infinity if mu of a naught is positive. So we must have that mu of a naught to be equal to 0. So this proves your Poincare recurrence. This is a complete proof, and so we saw how measured preservingness is being used. So this is a very useful property. So this type of techniques is being used in the whole of ergodic theory. This is a very, very basic result, and it's a very fundamental and non-trivial as well. So, and this is just a simple application of the finiteness of the measure and the measured preservingness of the transformation. So for infinite measure, this may not hold. Okay, so for infinite measures, this may not hold. For example, you take R, okay, you take R and you consider the transformation from R to R by translation, x going to x plus a. So you take x and you take some set over here for an a is positive, of course, and then for every x above a, quote unquote, it will drift towards infinity. Okay, so it will have x plus a, x plus 2a, and so on. So it will never return to this set a. So, and it's not happening because your measure of the whole space is not bounded or is not finite. So for infinite measures, Poincare recurrence fails. So for infinite measure, you can't have a Poincare recurrence thing. Okay. So now let me just give a brief introduction to other ergodic theorem, which is called the Birkhoff Ergodic theorem. I'll come back to this theorem later. But I'll just state it now. So Birkhoff Ergodic theorem states that if you have so you have this dynamical system, right? And let's say you have another measurable function from x to r. Then the Birkhoff Ergodic theorem states that if you look at this quantity, f of ti of x, this exists, and it also have a limit. It also has a limit, and that limit is well known. But I don't know whether I should state this or not. But this is something which is a very advanced stuff, because I think for understanding this you need a concept of conditional expectation. This is something which is like the conditional expectation of f with respect to a sigma algebra, and this sigma algebra is something which is called an invariant sigma algebra. So yeah, I don't want to talk about this. So this is a very beyond the scope stuff, I think, at the M.Math level. So just ignore. So just I think for the time being, you can just assume that the limit exists, and this quantity you can just ignore.
One more thing, the sum is up to n minus 1 or n, I think, right?
Yeah, right. Thanks. So who is this? Is it Ritik? Hello? Is it Ritik? Okay. Okay, so can you hear me? Hello?
Yeah, we can hear you.
Okay. So yeah, so this is the Birkhoff Ergodic theorem. So he states that this quantity, you know, have a limit, and this limit is this. But I don't want to talk about the properties of this, the value of the limit, because it involves a lot of other stuff that I need to introduce. So for that, you can just ignore. But uh, yeah, so maybe I'll come back to this later. So now I'll move on to a very special, a very important topic, which is called ergodicity. Yeah. So, okay. So now, if you have any questions, just please ask now about the other topics that I discussed earlier, or if you have any comments, any further questions, if you have, just let me know.
Yeah.
Even here.
Yeah. So in the like the last theorem we did,
Okay.
so that first of all you discussed that the possible motivation was we consider the f to be the indicator function, that that the point belongs to some set A.
Right. Right.
Then if we set f to be the indicator function, so what does this? Is there some nice form of the expectation?
Yeah.
So
Yeah.
like,
Yeah.
what's the answer of that
Yeah.
question?
Right. Very nice question. Very nice. So suppose you have, so this f is measurable. Okay. This f is measurable. And sometimes you can also replace it by some integrability L1, L2, so that I don't want to discuss. So suppose you have this indicator function A. Okay. Now if you look at this quantity, uh, it's like, so that's nothing but uh, indicator of A of Ti of X. So if you uh, sort of write it another way, you will see this is nothing but indicator of A of X. Okay, just a basic algebraic manipulation. Okay, so now the question you ask is, does it have a nice limit? The question is yes, if P is ergodic. So now that I was about to discuss what ergodicity means. So if T is ergodic, then you have a nice limit. If T is ergodic, then this converges to mu of A, the measure of A. So if T is ergodic, then you have a nice form. For general measure preserving transformation, you don't have such things. But I haven't told you what an ergodic thing is. So I was about to come to this point later, but you already asked this question. So my next topic was ergodicity. So after discussing ergodicity, then you can understand what I wrote over here.
Okay,
Okay.
thank you.
So it's a very nice question. Yeah, very natural as well. You know. So now, people say this concept of ergodicity came from prime numbers. So initially, I was quite confused how some definition of dynamical system come from prime numbers. Then I think around maybe I think 1 year back, I saw a lecture by someone. There I understood how it's related to prime numbers. It's nothing related to prime numbers. It's actually related to something is called breaking a system into further systems and all. So if you have a prime number, you cannot break it into further composite numbers and all. So ergodicness is also something like that. So I'll just discuss what an ergodic theory is. So let's say, let me call it ergodicness, you know, or ergodicity, whatever you can call it. So suppose you have a dynamical system. Okay, suppose you have a dynamical system P, and suppose you have a space. Okay, suppose you have a space X, and suppose you have another set A, such that T inverse of A is equal to A, and mu of okay. and mu of A, and mu of A is between 0 and 1. Okay, so you have A and A complement. Okay. So you have A and A complement. Then you can define another measure. Is called, say, A bar of, let's say, mu A. So we'll define two measures, which is mu A and mu A complement. So mu A is nothing but the conditional measure. So it's nothing but mu of A intersection B by mu of B, and mu of A complement B is nothing but mu of A complement intersection B and mu of B. Okay, so you have these two measures coming out of your original measure. So we'll show that. So we'll show that. So we'll show that both mu of A and mu of A complement are measure preserving. So I'll show it for once for only mu of A. Then you can, I think, check for others. So if you have a T inverse of B, is nothing but mu of T inverse of B intersection A over mu of A. And then if you move along, you have mu of T inverse of B intersection T inverse of A by mu of A. Now this happens because, this happens because you assume this. So now this is nothing but mu of T inverse A intersection B by mu of A. Now you use the measure preserving property of mu. You have mu of A intersection B of mu of A, so which is nothing but mu A of B. So we got mu A of P inverse of B to equal to mu of A of B. Okay, so mu of A is measure preserving. So mu of A is measure preserving transformation. So similarly, just by this following the same argument, you can show that mu of A complement is also measure preserving transformation. So initially you have a measure preserving transformation mu, and you broke it down into two other measure preserving transformation, mu of A and mu of A complement, right? So you have a measure preserving transformation, and you broke the measure preserving transformation further into another two measure preserving transformation, T1 and measure preserving transformation T2. So
I have a doubt here. Mu
These
is the
are
measure, right?
right. These are measures, right? These are not
mu,
transformations.
No. Yeah. Mu are measures. Only T is the transformation.
Yeah, and one more thing. Here you wrote T inverse of A is equal to A. Top
Right.
of the page.
Right. Yes.
Are we using? Where are we using that thing?
No. We are not using that. I'm just trying to motivate the definition of ergodic.
All right.
Like I'm just trying to use it, motivate the definition of ergodicness. I haven't defined what ergodicness is. So I'm just saying, if you have T inverse of A equal to A, and you have this, then you can break your measure preserving system into two further measure preserving systems. So that's what I've done till now. Is it clear?
Okay. We are basically checking whether T is measure preserving transformation with respect to these measures.
Right.
Mu of A and mu.
Right. So we just prove that mu of A and mu of A complement is measure preserving transformation, right? So you have a measure preserving transformation, and you showed, like, if you have this condition, if you have these two conditions, T inverse of A equal to A and mu of A equal to, and so for this condition, we showed that we can break our measure preserving system into two further measure preserving systems, right? But so in some sense, this measure preserving system is reducible. Like we don't like reducible systems. So we like to have some definition which will not allow such breaking down of systems. So and that motivates the definition of ergodicness. So can anyone tell me, like, like, like what? Suppose we have this T inverse of A equal to A. So like what condition will prevent me from breaking my system into further smaller systems?
So if we take the condition that for those sets where T of A is A,
Either mu of A equal to 0 or mu of A equal to 1, then you can't further break down your system, right? Okay. So that prompts the definition of ergodicness. So in ergodicness is in some sense it do not allow your system to break it further into further measure preserving systems. So that motivates the definition of ergodicness. Okay. So suppose you have a dynamical system. Okay. Suppose you have a dynamical system, and we say, this is the definition. We say T is ergodic if for all A such that T inverse of A is equal to A, we must have either mu of A equal to 0 or 1. So this is the definition of ergodicness. So as someone else said, like when you have such good convergence, so when your T is non-reducible, that means T is ergodic, then you have this kind of convergence. So that is a very beautiful result, I think, in ergodic theory. And so people, so since you cannot break down your system into further other system, people say that this ergodicness is related to the concept of prime numbers. But I think that that's a very vague connection. It's just a connection in a philosophical level, nothing mathematical. So yeah, so this is the definition of ergodicness. Okay, so now we'll look at examples. Okay, so now we'll look at, okay. So can anyone tell me how many minutes I have left, or how many minutes I have used? Anyone? It was a
You have almost like half an hour left.
Oh, okay, very nice. Cool. Okay. Okay, so yeah, so then I think I can talk a lot of things. Okay, so now this is called a characterization of ergodicness. Characterization of ergodic measures. So okay, so this is one of the theorem. So suppose you have a dynamical system. Okay, so this is a dynamical system, and you want some characterization, like when can you say like your T is ergodic. Okay, so every time checking this definition may not be a very efficient way of going with it. So you need some characterization, and this is this kind of technique is all over mathematics. You have some definition, you go by a lot of equal characterizations, and then you apply all this characterization to solve various problems. So let's see if we can find a characterization, and then we'll apply it to maybe solve one problem, which is a very important problem. So So what's the characterization? So T is ergodic. So your T is ergodic if and only if we have F compose T equal to F, then this will imply, like for all F measurable, this will imply that F is constant almost surely. It's constant almost surely. This is the equivalent criteria. So T is ergodic if and only if this holds. So this is called FT characterization, something like that. Okay. So now we'll prove this. It's a very easy things to prove.
F is arbitrary. What is it?
Yeah, F is measurable. F is measurable, and if you want, you can also restrict it to L1 or L2.
No, I mean, what is the statement actually that there exists some F such that this holds, or for all of these holds?
Oh, for all F. So if you have T to be ergodic, then for all F such that this hold, we must have that F is constant almost surely. And if you have for all F measurable, this condition holds, and that implies that F is constant almost surely, then we'll have that T is ergodic.
Can you explain what will be the domain and range of this F? I mean,
Yeah, sure, definitely.
Yeah, that
sure,
thing will.
Yeah. I think I should mention that. Thanks. So I have X and X, so T, and F is just a function from X to R. Okay. So this is your F of T, and this is your F. So domain is over here. So over here you have domain X and range R. So similarly F, you have domain X and range R. So is it clear?
Yeah. Now it's clear.
Yeah, I think I should have been more careful writing this one. Yeah, I think I should have been more careful writing this one. So we'll prove this. Don't worry, we'll prove this. So maybe while proving, all things will get clear. So since I have time, so I'll prove this. So let's say this one. Suppose we have like if F compose T is equal to F. Suppose then this implies F is equal to constant almost surely. Suppose we have this, okay, like this condition. So now we have to prove that T is ergodic. So suppose to prove T of ergodic, suppose we have a set such that T inverse of A equal to A, then we are required to show. That mu of A is equal to 0 or 1, right? So if we can show this, then we are done. So since okay, so suppose so now we have to come up with an F. Okay, so what is a natural choice of F? Anyone? If you can guess, what's the natural choice of F? Anyone can guess? Let's see.
Indicator.
Yeah, right. A very natural guess. So if you have F to be an indicator, so suppose you take F to be indicator. Okay, since it's a finite measure and A is measurable, definitely F is measurable and it's also L1 and L2, right? It's finite. So now look at F compose of T. So that is indicator of A compose of T. So now check is very easy to check. This is nothing but T inverse of A, right? And now T inverse of A is equal to A. So that is nothing but indicator of A. Now what is indicator of A? That is F, right? So this condition is satisfied, right? This condition is satisfied. This will imply your indicator of A is constant almost surely. But indicator of A can take only two values, right? So either indicator of A is equal to 1 almost surely, or indicator of A is equal to 0 almost surely. right? So in case you have indicator of A equal to 1, so case 1, when you have indicator of A equal to 1 almost surely, then measure of A is nothing but integration of x over A of du, and this is equal to 1, so this is nothing but mu of x is equal to 1. And for other case where you have mu of A equal to 0, almost surely, then you have, by same argument, okay, that mu of A is equal to 0, right? So we proved one direction. So this direction is proved. If such condition hold, then T has to be ergodic. Okay, because if you just go over the proof, right, it's very easy and natural proof, I think. Okay. So now let us look at the reverse. So reverse is a bit complicated, not complicated, I would say it's tricky, I would say. Now, so it's okay. So now here is the reverse part. Now suppose T is ergodic. Okay. Now suppose T is ergodic, and you have F composed of T is equal to F. Then we are required to show is that F is constant almost surely, right? Now since a tricky proof, so I'll just do the proof and you will see how. So now you define A of T as sort of a set of all x such that f of x is greater than t, let's say. Okay, so you fix t in a real number, and you define A of T as set of all x such that f of x is greater than or equal to t. Now so now note that T inverse of AT is nothing but set of all x such that okay, 1 minute, yeah, just 1 minute. Okay, yeah. So now you can write AT as set of all x such that f composed of t of x is greater than t, right? So this is by using this fact. It's nothing else. You just use this fact. Now this implies that this is okay. Okay, okay, just I think this 1 minute. Yeah. Okay. So now this is nothing but, if you look at it, T inverse of A of T. Is it sort of clear how is it T inverse of A of T? It's just by the sort of definition. Okay. Just by the definition of the T inverse of a set. So since A of T is equal to T inverse of AT, then by ergodicness you have like mu of AT is either 0 or 1. Okay, so now note that mu of AT goes to sort of 0 as t going to infinity. Okay. since you're just, since you're taking this set t to infinity and you're sort of increasing t, so it's going to converge to an empty set. So this measure is going to be 0. So you can take C star to be, I think, the infimum of t, such that mu of at to be equal to 0. Then you can show like this f is equal to C star, almost surely. So this is the proof of this characterization. This has been a bit rough, but if you check it, this is quite okay. So yeah, so this is a characterization. Okay, so now you will, so maybe now I'll give one example of a very important ergodic transformation. That is irrational rotation. Okay, this is an example. So here I'll use a bit of Fourier analysis. So maybe because I don't know how to do the proof without using Fourier analysis. So, but like whatever stuff I write using Fourier analysis will be very trivial. But like how the results came in, for that you might have to do a course in Fourier analysis. So yeah, just go via that. Okay. So if you have any question, like how it's coming and all, just ask. So yes, so irrational rotation. So irrational rotation of the circle. So we'll prove that the irrational rotation of circle are ergodic. Of the circle are ergodic. So this is probably my last proof before I end. So so your t theta is your math from rz to rz. So so you have your x and you're sending it to x plus theta, where theta is irrational. Okay, so your theta is irrational. So now, so here we use something which is called Riemann-Lebesgue lemma. Okay, so this is from Fourier analysis. So fact from Fourier analysis. You can just ignore or you can just take it by faith, whatever I'm saying. So f, if f is L1 and periodic, then if we look at its Fourier expansion, then we'll have a Fourier expansion, I think. So yeah, so n belong to z, an e to the power I 2 pi nx. Then if you compose it with t, so you have sum over n belong to z, an e to the power I 2 pi n x plus theta. So you have x plus theta. So that is nothing but nz an e to the power I 2 pi n theta times the power I 2 pi nx. So now since we are assuming this to be equal to f, so this is nothing but an e to the power I 2 pi nx, n belongs to natural number. Sorry. And since these two series, since these two series are equal, so their coefficients have to be equal. So an is equal to an e to the power I 2 pi n theta. The theta is irrational, remember. So since theta is irrational, this quantity is never zero. This quantity is never zero. So note for any For n equal to 0, you're fine. For n equal to 0, this is 0. So you have a0 equal to a0 to the power I 2 pi 0 times theta. So this is 1. Okay, this is 1. So you are fine. But for a not equal to 0, you must have an to be equal to 0 because theta is irrational, as theta is irrational. So we must have that f is equal to a naught. Let's say almost surely.
What
So in
was
the
your assumption on f? It was
f was L1. F was L1 and periodic because we are considering continuous function on circle. So on circle, like you have periodic function, right? Circle. So f is L1. Yes.
does L1 give equality of coefficients? I'm not
So,
sure.
yeah. It's a fact from Fourier's, I think Fourier analysis. So if you have two Fourier expansion, the coefficients have to be equal. Okay. Coefficients have to be equal. So these are
Was
all.
there any assumption made for t?
Yeah. T is measure preserving. Like T is irrational rotation. So here is your T. So T is irrational rotation, and we
Okay,
proved
because
in
of
our
this irrational theta, it's becoming ergodic, right?
right. Yes, because of this theta being irrational, this quantity is never 0. Okay. So are you getting it? So because as theta is irrational, so e to the power I 2 pi n theta is never equal to 0. So that's the reason you're only having f is equal to, like, only your a0 is may not be 0. All other ans have to be 0. So your f must be equal to a0 almost surely, because your theta is like irrational.
I think you mean e power that is not equal to 1.
Mm-hmm. Mm-hmm. Hello. What? Can you repeat? Yeah. Not be equal to 1. Yeah,
Hello?
exactly. Right. Sorry.
Can you
Right.
get it?
Yeah. Sorry. Yeah. Thanks. Yeah. Thanks. Yeah. I was doing stupid things. Yeah. It's not equal to 1. Right. Yeah. Exactly. Yeah. Right. Yeah. Thank you. Yeah, so it's not equal to 0. It's not equal to 1. Now it's getting clear. So now, do you have any questions? Anyone about the proof and all? It's a very rough proof. It's very hard to do, I think, without Fourier analysis. With Fourier analysis, you can just very small, very small proof. Okay, so now I'll just end maybe. So this is an exercise that you can try at home. For if theta is rational, prove that T is not ergodic. T is not ergodic. For any rational, T is not ergodic. So this is maybe an exercise that you can try. It's very easy exercise. So if you want some hint, also I can give you. So now I think I have maybe 5 minutes or so. So I'll just now talk about the last. What are the things to study and all. So okay. So like other extra things that you can study, you can say. So this ergodic is a very I would say, is a very naive, not naive, and it's a very fundamental concept. Okay, so there are other concepts as well of like higher ergodicness and all. They are called mixings. So I'll just try to draw an analogy between probability theory and ergodic theory. So you have ergodic theory over here, and you have probability theory. Okay. So here you have convergence in distribution. You have convergence in distribution. You have convergence in probability, and here you have convergence in almost sureness, right? So this convergence in almost sureness implies convergence in probability. Convergence in probability implies convergence in distribution. So here in ergodic theory, you have something called like ergodicness, Then you have something called weak mixing, and you have something called strong mixing. Okay. So the strong mixing will imply weak mixing, and weak mixing will imply ergodicness. So this. So this is the analogy between ergodic theory and probability theory, and this mixing concept is very much useful in Markov chains and all. This sort of relates to the asymptotic independence of stochastic processes. So yeah, so this was my 2 cents on this introduction to ergodic theory. It's a very basic introduction. I think I just did some very basic stuffs. So it's a very delicate and vast subject, and a lot of research are being done on this. And primary reasons are like it has found a lot of applications in even complex analysis, number theory, function theory, and all. So I've also given references. You can look at a very famous book. It's called Introduction to Ergodic Theory by Peter Walters. It's a very wonderful book. I learned most of the stuff from them there. So you can have a look at it. So yeah, so I end my talk, and so thank you. So if you have any question, please ask. I'll be happy to answer. Thank
So
you.
what does mixing mean?
Okay, so mixing means in sort of no, I can't give you the actual definition right now. It's sort of asymptotic independence. So it means, so let's say you have some systems going over time. So you have systems going over time. You're seeing some systems at times. So mixing means if you are far apart. So here you have some time set A, and so if you are far apart in time, so this is the distance, okay, this is the distance. So if you are far apart in time, that means you are getting more and more independent. So mixing is like that. So as you go away from your initial system, the contribution of your initial system doesn't matter. So when you look at the definition of mixing, it just tries to capture that idea. So now I recently read a paper that was suggested to me by Parthenil Roy. He said, so I read one of his papers on some large deviations of some continued fractions. So there they introduced some another mixing concept called exponential mixing. So exponential mixing means you have this rate of asymptotic independence in an exponential rate. So this mixing basically means that as you go far apart in time, you get more and more independent. So yeah, that's it. So yeah, that's I think the only motivation I
Okay.
will give.
So you said that mixing implies ergodicity, right?
Yeah, yeah.
So can you give an intuitive idea? I don't see how immediately how ergodicity follows.
Yeah, right. Yeah, even so actually that mixing gives ergodicness. It actually comes from the way it's defined. Okay, so intuitively, I think even I'm not sure how it's done, but
Oh, okay, okay.
because
Thank you.
but if I can give you the definition of weak mixing, then you will see that that definition implies ergodicness. So that will take some
Oh,
time. Okay.
oh,
Okay. Any other questions? You can also ask me later. You can WhatsApp me or whatever if you want to read further. I'll be happy to discuss.
Can you explain what are some consequences of that irrational rotation thing? That theta being ergodic?
Okay, irrational. This is actually a very I don't know what is the consequence, but I think the fact itself is quite beautiful. I don't know what are the consequences, but the fact itself, mathematicians prove beautiful results, right? They may not have good implications, but uh, yeah, right now I don't know what are like the consequences and how you can use that. maybe there are some use. Like I'm not aware of that. I mainly try to understand, this concept of ergodicity, like how it's getting used in probability theory and all. But I haven't seen right now, like how this irrational rotation thing is useful. But I think while you are proving the ergodicness of the irrational rotation, the proof technique that you use for your analysis, that's quite actually useful. Okay, sometimes you prove results in mathematics because you try to understand like how you prove things, and then you try to imitate that proof idea to your other proofs. So yeah, that's the answer. So if anyone has other questions, you can hear me, right?
Okay, one more thing, like we did that. You said in a circle, if you consider the like if you translate by an irrational, right? So we get yeah. So basically, so if you consider flows on, let's say, a sphere with a similar concept like irrationality, so does ergodicity still follow?
Right. Yeah. So then you have to define what you mean by irrational rotation in sphere.
Yeah, yeah, yeah. Hmm.
So that I don't know how you can define
I see.
that. So maybe if you can define, I'm sure maybe yeah, definitely all the results that I've shown for R, it definitely holds for Rn. This characterization all definitely holds for Rn. So and I don't know. Yeah, I think you definitely have some Fourier analysis technique for higher dimension. So maybe you can use them. Yeah, I'm not aware of that. But I think first step would be to define an irrational rotation for sphere. What do you mean by it? I don't know if anyone can have idea. What do you mean by irrational rotations?
Yeah, I see the problem. Yeah.
Any other question? Okay. Any comments? Maybe.
Okay, looks like there are no comments, so let's end the talk.
Okay.
Uh, Thank you for giving the talk. It was amazing. So
Okay.
I'll stop the recording now.
Okay. Sure.